Good afternoon, everybody. I have a new paper here called The Dimensionless Quantity, Connecting Sun-like Stars to Red Dwarfs on a Mass Radii Diagram. I call it the Cassandra Ratio. Now, my dad introduced me to the concept of Cassandra. Basically, it's a mythology here. I'll read it out to you. Here's a picture of Cassandra by Evelyn de Morgan. As you can see, she's pulling her hair out with frustration, I take it. The Cassandra ratio, I call it the ratio, but it's really the Cassandra term originates in Greek mythology. Cassandra was a daughter of Priam, the king of Troy. Struck by her beauty, Apollo provided her with the gift of prophecy. But when Cassandra refused Apollo's romantic advances, he placed a curse, ensuring that nobody would believe her warnings. Cassandra was left with the knowledge of future events, but could neither alter these events nor convince others of the validity of her predictions. And that's the same with the sun. I cannot alter the sun's future. It's well beyond my capacity as a human being. As well, it's incredibly difficult convincing people that the sun isn't going to expand into this fantastic red giant that's going to swallow the inner solar system. I find that to be improbable because, for one, red giants are extremely rare, and even if they are actual red giants, if they're fantastic size, then weird mechanisms have to be used to invoke why they should be expanding so large. What's more likely is happening is that the sun-like stars cool, shrink, and die along a simple line of evolution, and this specific ratio has to do with stars between 1 solar mass and 1/2 solar mass. It doesn't apply to all of them, just this little narrow band. But the narrow band is important because it connects sun-like stars to red dwarfs, which are extremely numerous. And as we'll see with Kepler data, and as we'll see with the test data that comes in, the stars, as they cool, go along this simple line right here. It's almost linear, if you will. It's a line of best fit. But most importantly, the flaring and shrinking happens alternatively. So, well, also can mean, simultaneously, but alternately flaring and shrinking. So if it moves down, it's flaring, and if it's moving to the left, it's shrinking. So what happens to the star, this is really big and hot like the sun, it collapses, flares, collapses, flares, collapses, flares, collapses, flares. And it does this repeatedly over many millions and millions of years. And we see it happening inside of what are called flare stars, the red dwarfs. But flaring happens alternatively with shrinking, and it happens sometimes the same way, same time. But for the most part, as the star flares and shrinks, it does so along the line of best fit. So if it's too far down here, it'll shrink and go past that line. If it's too far up here, it'll flare and go past that line again, and it will keep on adjusting itself as it evolves. So that being said, this is far beyond establishment's acceptance of the sun-like stars expanding into red giants. This is not going to happen. They're losing their mass, they're cooling, and they're shrinking, and they're differentiating their interiors. And after this ratio ends at the very end and becomes a smaller, cooler red dwarfs, and then there's going to be obviously a different type of ratio involved, and the mass loss is going to vary significantly because then their mass loss can be more dependent upon how close they orbit to a hotter host, and if they orbit far away, or if they're rogue objects and they freeze over and they don't lose mass very much, and then they age considerably, building their cores in the center a lot more, making larger Earth-sized objects. It can vary significantly as time progresses when you go beyond this ratio area down here. So this is basically a very stable area. This is taken from the paper, The Island of Stellar Stability. I took this graph from that, but this is a new paper itself. I'll link this to the bottom. Yeah, I just thought I might as well put some math in there just for the hell of it. And it's a dimensionless quantity, so there's no dimensions involved. It's like the Reynolds number. There's not a dimension, just a set number. It's 0.0096. And, I put that on this paper here. All right, y'all. Take it easy.